Let me ask you something. If I give you a short, thick piece of wood and tell you to push down on it as hard as you can, it probably won't do much. It just sits there. Maybe it compresses a tiny bit, but nothing dramatic happens. Now, imagine I hand you a long, skinny stick. Could be a chopstick, could be a metal ruler, could be one of those cheap plastic rods from a clothes rack. You push down from both ends, and what happens? It suddenly bends sideways. Sometimes it snaps, sometimes it folds, sometimes it looks perfectly fine for a second, and then boom, it gives up instantly. Now here's the weird part. A lot of people look at that and think, well, obviously the skinny one is weaker. Not exactly. And this is where structural engineering gets really interesting. Because sometimes a structure doesn't fail because the material isn't strong enough. It fails because the shape becomes unstable. That's a completely different problem. And honestly, it's one of the scariest failure modes in engineering, because it can happen fast with almost no warning. And today, we're talking about member stability. Or in simpler terms, why straight things suddenly stop being straight. And yes, this is way more important than it sounds, because this idea affects buildings, bridges, scaffolding, transmission towers, cranes, stadiums, and even furniture in your house. Anywhere you see long structural members carrying compression loads, stability matters a lot. Let's go back to the chopstick example. Imagine you place a chopstick vertically on a table. Now, press downward slowly. At first, nothing happens. The chopstick looks fine. Everything seems stable. You press harder. Still okay. Then suddenly, it bends sideways. That sideways movement is the key. The chopstick didn't crush. The wood didn't reach its compressive strength limit first. Instead, the member lost its ability to remain straight. That phenomenon is called buckling. And buckling is one of the biggest reasons compression members fail. This is where beginners often get confused. They think failure equals breaking. But engineers know failure can happen in different ways. A steel member might yield, concrete might crack, a beam might bend too much, and a column might buckle before the material itself is even fully stressed. That's wild when you think about it. Imagine buying a car that shuts down before the engine reaches full power. That's basically what buckling does. The structure quits early, not because it ran out of strength, but because it ran out of stability. And this happens in real life more often than people realize. Take construction scaffolding. You've probably seen temporary steel pipes holding platforms. Those members often look simple, just vertical steel rods. But if those rods are too slender or installed incorrectly, they can suddenly buckle under load. That's why scaffold collapses can happen so quickly. Same thing with high-rise buildings during construction. Before all the bracing systems are installed, some structural members can be vulnerable. That's why engineers care about temporary stability just as much as final stability. Even famous structural failures have involved stability problems. And what makes these failures dangerous is how sudden they are. With some failures, you get warning signs: cracks, noise, visible deformation, slow deterioration. But stability failure, sometimes it's basically looks fine, looks fine, looks fine, collapsed. That's terrifying. And it's not limited to giant structures. You can test this at home. Take a sheet of paper, hold it vertically, push downward from both ends. It buckles instantly. Now, roll that same paper into a tube. Push again. Suddenly, it can carry much more load. Same material, same paper, different geometry. That should tell you something very important. In structural engineering, material strength is only part of the story. Geometry matters. Length matters. Shape matters. Support conditions matter. And all of those things influence stability. This is why engineers can't just say, "Oh, steel is strong, we're good." No, that would be a disaster, because steel can still buckle, concrete can still buckle, Wood can still buckle. Any compression member can become unstable if poorly designed. And this becomes even more important as structures get taller. Think about skyscrapers. Burj Khalifa didn't become the tallest building in the world just by using stronger materials. Its engineers had to think carefully about stability, wind stability, column stability, overall structural stability. Because as structures get taller and slimmer, stability becomes harder to control. The same thing applies to bridges, communication towers, cranes, industrial plants, basically anything tall, thin, or heavily loaded. And here's the funny part. Most people notice structural failures only after something dramatic happens. A bridge collapse goes viral, a crane falls over, a building partially fails. Then people say, how did engineers not see this? Trust me, engineers think about stability constantly. That's why structural design calculations can get so detailed, because preventing instability is a huge part of keeping structures safe. And this topic becomes even more fascinating when you realize there's actual math that predicts when a member will buckle. A famous mathematician named Leonard Euler.
So now we know something important. Just because a structural member is made from strong material doesn't mean it's safe. That sounds weird at first. People hear steel and automatically think strong, reliable, almost unbreakable. But structural engineers know that's not how real life works, because sometimes failure has nothing to do with the material being weak. Sometimes the material is perfectly fine. The real problem is that the member can no longer hold its shape. And that's what stability is really about. Very simple definition. Can a structural member stay in its original position when load keeps increasing? That's it. Can it stay straight? Can it stay balanced? Can it keep doing its job without suddenly deforming? If yes, it's stable. If no, you've got a serious problem. And the dangerous part, a member can look completely fine right before stability failure happens. That's what makes this topic so scary. Let me give you an example. Imagine you're standing an empty soda can on a table. If you press straight down on the top gently, it can actually support a surprising amount of weight, more than most people expect. But the moment there's a tiny dent on the side, or your hand pushes slightly off center, the can suddenly crumples, instantly. That's stability failure. The aluminum didn't suddenly become weak. The shape lost control. And once that happens, failure happens fast. Same idea with structural members. Think about a tall steel column inside a building. At first, everything looks normal. Load increases, the column compresses slightly. No big deal. Still looks straight, still looks safe. Then maybe there's a tiny imperfection. Maybe the column wasn't installed perfectly straight. Maybe there's a small manufacturing defect. Maybe the load isn't perfectly centered. Maybe wind adds a little horizontal movement. And suddenly, that tiny issue gets worse. The column bends slightly. That bending creates more stress. That stress causes more bending. And now, things start snowballing. Before you know it, the column suddenly buckles. And people watching might think, that came out of nowhere. But engineers know it usually starts with very small imperfections. And here's the truth nobody tells beginners. Perfect structures do not exist. In textbooks, everything looks perfect. Perfect columns, perfect loads, perfect connections, perfect geometry. Real life? Not even close. Construction workers are human. Materials have imperfections. Weather affects installation. Loads shift. Things move. That's why engineers design for reality, not fantasy. And stability design becomes incredibly important because real structures always have imperfections. Think about balancing a broom vertically on your hand. It's hard. You move a little, the broom moves a lot. Eventually, it falls. Now, place that broom flat on the ground. Way more stable. That simple example explains structural stability better than most textbooks. Some systems naturally resist disturbance. Some systems become unstable very easily. Now, let's bring this into real buildings. Look at skyscrapers. Burj Khalifa isn't just standing because the concrete is strong. Its entire shape was designed to stay stable against gravity and wind. Without proper stability design, that building would have huge problems. Same thing with bridges. Look at Golden Gate Bridge. That bridge constantly deals with traffic loads, wind loads, temperature changes, vibration. Its designers had to make sure those members remained stable under changing conditions. And then there are construction failures. This is where stability problems become deadly. Temporary supports, scaffolding, steel frames under construction. These systems sometimes collapse before the final structure is even complete. Why? Because temporary stability wasn't handled properly. The finished design may be perfectly safe, but during construction, a missing brace can create disaster. And that's something most people never think about. A building isn't only vulnerable when it's old. Sometimes it's most vulnerable while it's being built. And here's another misconception. People often think bigger means safer. Not always. A massive member can still fail if stability is ignored. Meanwhile, a slimmer member can perform incredibly well if designed correctly. That's why engineering isn't just make everything thicker. That would waste insane amounts of money. Good engineering means using material efficiently while keeping the structure stable. That balance is hard. And that's why structural engineers spend so much time analyzing this stuff, because stability failure is brutal. It doesn't always give you dramatic warning signs. Sometimes it's just looks fine, looks fine, looks fine, and then suddenly, failure. That's why stability is one of the most important concepts in structural engineering. It's not just about whether something can carry load. It's about whether it can carry load without losing control of its shape. And in the next part, we'll break down what actually makes a member more likely to buckle, because length, shape, and support conditions can completely change everything.
So now we understand the big idea. A structural member can fail even when the material itself is still perfectly strong. If it loses its shape, if it starts bending sideways, if it can't stay stable under compression, it can fail fast. Now, the obvious question is, what actually makes buckling more likely? Why do some members stay stable under huge loads while others fold like cheap lawn chairs? And this is where structural engineering gets really practical. Because once you understand the factors behind buckling, you start noticing them everywhere. And the biggest factor of all? Length. Yep. Sometimes being tall and skinny is a structural disadvantage. Think about trying to break a short pencil. Pretty difficult. Now grab a long fishing rod. Way easier to bend. That's basically what happens in structures. Longer members are usually more vulnerable to buckling because they have more room to bend sideways. Short columns tend to fail by crushing. Long columns tend to fail by buckling. And engineers are constantly trying to find the balance. Too short and bulky, you waste material and money. Too long and slender, you create stability risks. And this leads to one of the most important ideas in structural engineering: slenderness. That's basically the relationship between length and thickness. A very long member with a small cross-section? Dangerous. A shorter, thicker member is usually more stable. You see this all the time in real life. Take a drinking straw. Hold it vertically and push down. It bends easily. Now compare that to a thick cardboard tube. Much harder to buckle. Same concept. Now let's talk about shape. This one surprises people. Two structural members can use the exact same amount of material and perform very differently depending on shape. That's why structural steel comes in different sections: I-beams, box sections, circular tubes, channels, angles. These shapes aren't random. Engineers choose them for efficiency. For example, hollow steel tubes can be extremely good at resisting buckling. That's why you see them in towers and truss systems. And I-beams? They're great for certain applications because they place material where it helps most. Shape matters way more than most people realize. Then there is material stiffness, and this is different from strength. People mix those two up all the time. Strength answers, how much stress can this material take before failing? Stiffness answers, how much does this material resist deformation? Very different. For example, rubber can stretch a lot. Steel resists deformation much more. That's why steel is commonly used for major compression members. Wood can work too. Concrete can work too. But each material behaves differently. Engineers need to understand those differences. Now, let's talk about connections. This one gets ignored by non-engineers. People look at columns and beams. They rarely look at the joints. Huge mistake. Connections can completely change stability behavior. Imagine trying to stand while your ankles are loose and unstable. Pretty hard. That's what weak connections can do to a structure. A column that's firmly connected at both ends behaves very differently from one that can rotate freely, even if the column itself is identical. That's why connection design is such a huge deal. Bad connections can ruin good structural members. Then we have lateral support. This is massive. Imagine holding a ruler vertically. Easy to bend sideways. Now, imagine your friend places their hand in the middle to stop sideways movement. Suddenly, it becomes much harder to buckle. That's lateral bracing, and buildings use this idea everywhere. Braces, walls, floor systems, cross members, trusses, all of these can help prevent unwanted movement. Without proper bracing, tall structures become far more vulnerable. This became very obvious in Tacoma Narrows Bridge collapse. That disaster involved aerodynamic instability, which is a little different from column buckling, but it showed how dangerous instability can be when movement gets out of control. The bridge looked dramatic because it twisted violently before collapsing, and people suddenly realized stability problems can destroy massive structures. Wind is another major factor, especially for skyscrapers. Look at Shanghai Tower. Its twisted shape helps reduce wind effects. That wasn't just for aesthetics. That design choice improves performance. Modern skyscrapers often use shape to fight instability. Pretty smart. And then there's construction quality. Even perfect design drawings mean nothing if execution is terrible. A slightly crooked installation, missing braces, poor welding, wrong boat placement, all of these can create stability problems. And that's why engineers inspect construction sites so carefully, because tiny mistakes can create huge consequences. And here's the bigger lesson. Buckling usually isn't caused by just one thing. It's often multiple small weaknesses stacking together. Too slender, poor connections, weak bracing, unexpected loads, construction mistakes, and suddenly you've got failure. That's why structural engineering is basically controlled paranoia. Engineers constantly ask, what could go wrong? What if this load changes? What if wind increases? What if this member bends? That mindset keeps people safe. And in the next part, we'll look at real-world collapses where stability failures turned into major disasters.
Up to this point, stability might still sound like a classroom topic. Columns, buckling, compression members, engineering theory. And honestly, that's how a lot of students first see it. Just another chapter in a textbook. Until you realize this concept has caused real-world disasters. And when stability failure happens in real life, it can be brutal. Because unlike some failures that happen gradually, stability failures can be incredibly sudden. One moment, everything looks normal. The next moment, something folds, shifts, or collapses, and the entire structure can go down with it. That's what makes it so dangerous. Let's start with one of the most famous structural failures ever. Tacoma Narrows Bridge collapse. If you've ever seen the footage, it looks unreal. The bridge starts twisting and bouncing violently in the wind. Cars are stuck on it. The roadway moves like a ribbon. Then, eventually, collapse. Now, technically, this wasn't classic column buckling. This was aerodynamic instability. But it teaches the exact same lesson. When structural movement gets out of control, failure can happen fast. And what shocked people was how massive the bridge looked. Most people assumed big bridge equals safe bridge. Clearly not. Its design made it vulnerable to wind-induced instability. That collapse completely changed bridge engineering. Engineers started taking wind behavior much more seriously after that. Then, let's talk about construction collapses. These happen more often than people realize, and they usually don't make global headlines unless the death toll is high. Imagine a steel frame during construction. The final building design may be completely safe, but during construction, not all braces are installed yet. Not all floors are completed. Some members are temporarily carrying loads they weren't meant to handle alone. That's where things go wrong. A missing temporary brace, an overloaded section, a slight alignment issue. Suddenly, a column buckles. That triggers nearby failures, and now you've got progressive collapse. One failure starts a chain reaction. And chain reactions in structures are terrifying because they move faster than human reaction time. Workers often have seconds or less. Scaffolding collapses are another major example. You've probably walked past scaffolding and never thought much about it, but these systems rely heavily on stability. They often use slender steel members. If installation is poor, if braces are missing, if loads become uneven, those members can buckle quickly, and once one part fails, the entire scaffold system can come down. That's why scaffolding regulations are so strict in many countries, because failures have killed a lot of workers. And then there's formwork collapse. This happens when temporary systems holding wet concrete fail. Wet concrete is incredibly heavy. People underestimate that all the time. Before concrete hardens, temporary supports carry enormous loads. If those supports lose stability, collapse. And that can be catastrophic on major construction projects. Now let's talk about towers. Communication towers, power towers, temporary event structures. These often look lightweight, and that's intentional. Engineers try to use as little material as possible while maintaining safety. But if wind loads are underestimated or maintenance is ignored, instability risks grow fast. Even cranes can fail this way. A crane boom is basically a long structural system dealing with huge loads. If operators exceed limits or if setup is poor, you can get instability problems. And crane failures are incredibly violent. Then there are buildings that fail because someone modifies them improperly. This happens more than people think. Removing walls, changing load paths, adding unexpected weight, poor renovations. A building may be stable in its original design. Then someone makes unauthorized changes, and suddenly stability gets compromised. That's one reason engineers hate surprise renovations. And here's what all these failures have in common. The structure often gave people false confidence. It looked okay. It seemed strong. People assumed everything was fine. Then reality showed up. And this is why engineers are obsessed with worst-case scenarios. They're not being dramatic. They know what instability can do. Because once structural instability starts accelerating, there may be no easy way to stop it. That's why inspections matter. That's why temporary bracing matters. That's why construction sequencing matters. That's why maintenance matters. And honestly, a lot of disasters are preventable. Not all of them, but many happen because someone ignored warnings, cut corners,
skipped inspections, or assumed it'll probably be fine. Those 4 words have caused a lot of structural disasters. And in the next part, we'll talk about how engineers actually prevent buckling and stability failures before they happen.
After hearing all those collapse stories, you might be thinking, so how do engineers stop this from happening? And thankfully, this is where engineering gets really impressive. Because structural engineers don't just hope things stay stable, they actively design against failure. They assume problems can happen. Then they build systems that can survive those problems. That mindset is what keeps buildings standing. Let's start with the most obvious solution. Make members thicker. A thicker column usually resists buckling better than a thin one. Makes sense, right? A thick tree trunk is harder to bend than a skinny branch. Same idea. But there's a catch. You can't just make everything massive. That would be insanely expensive. Imagine building a skyscraper where every column is ridiculously oversized. You'd waste huge amounts of steel, concrete, money, and usable space. Developers would lose their minds. So engineers need smarter solutions. That brings us to shape optimization. This is why structural members aren't always simple, solid rectangles. Look at steel sections, I-beams, box sections, tubes, H-sections. These shapes are designed to maximize performance while minimizing material use. It's basically structural efficiency. Use less material, get better performance. That's good engineering. Take Eiffel Tower. It looks surprisingly light for something so massive. That wasn't accidental. Its geometry helps it stay stable while reducing unnecessary weight. Then there's bracing. This is huge, and you can actually see this everywhere once you notice it. Cross braces on construction scaffolding, diagonal members in towers, braced frames in buildings. These elements help stop sideways movement. Remember, buckling often starts when members move sideways. So engineers try to block that movement before it becomes dangerous. Even floor systems can help provide stability. Walls can help. Roof systems can help. Everything works together. And that leads to a major lesson. Structures don't survive because one member is strong. They survive because the entire system works together. Now let's talk about connections. This part gets overlooked by non-engineers all the time. People admire skyscrapers. Nobody stares at bolts. Nobody posts connection plates on Instagram. But connections matter a lot. Bad welds, loose bolts, poor detailing, weak joints. These can completely destroy structural stability. A perfectly designed column connected badly can still fail. That's why connection design is taken so seriously, and why inspectors spend so much time checking connection quality. Then there's construction sequencing. This one surprises people. A building might be completely stable when finished, but unstable halfway through construction. That's why engineers carefully plan construction stages. Temporary supports, temporary braces, load limits, installation order, all of that matters. You can't just randomly assemble a skyscraper like IKEA furniture. Construction sequence can literally determine whether a project stays safe. And then there's safety factors. Engineers don't design structures right at the failure limit. That would be reckless. They build in extra capacity. Because real life is messy. People make mistakes. Weather changes. Loads change. Unexpected things happen. Safety margins help protect against uncertainty. That's why structures can often handle more than their normal expected loads. And modern engineering software has made this even better.
Today, engineers use advanced computer modeling to simulate behavior. They can test wind effects, earthquakes, buckling risks, vibration behavior, load combinations, and they can catch problems before construction even starts. That's a huge advantage compared to older generations. Think about modern super-tall buildings like Shanghai Tower. That building deals with enormous wind forces. Its twisted design helps reduce wind loads. Its structural system was carefully engineered for stability. That building isn't standing because people got lucky. It's standing because thousands of design decisions were made correctly. And then there's maintenance. Even a perfectly designed structure can become unsafe if neglected. Corrosion, loose connections, damaged members, unauthorized modifications, these can all reduce stability over time. That's why bridges get inspected. That's why towers get maintained. That's why buildings need monitoring. Engineering doesn't stop after construction. And honestly, this is what makes structural engineering so fascinating. It's not just math, it's prediction, problem solving, risk management. You're constantly asking, what could fail? What if loads increase? What if something moves unexpectedly? How do we stop that? That mindset saves lives. And in the final part, we'll talk about why stability might be the most underrated concept in structural engineering and why most people never notice it until something goes horribly wrong.
By now, you've probably realized something. Stability sounds like a boring engineering term until you understand what it really means, and then suddenly it feels terrifying. Because stability failure is sneaky. A beam that's overloaded might sag. Concrete might crack. Materials sometimes give you warning signs. You might hear noises, see deformation, notice something is wrong. But stability failure? That can be brutally fast. A member looks fine, still fine, still fine, and then suddenly it bends sideways, folds, or triggers a full collapse. That's what makes it so dangerous. And honestly, that's why engineers respect this topic so much. Because stability teaches a very humbling lesson. Strength alone is never enough. That idea applies everywhere in structural engineering. You can use incredibly strong steel, high-performance concrete, advanced materials, amazing construction technology, and still fail if the structure can't stay stable. That's why engineers don't just ask, how strong is this material? They also ask, how does this member behave under real-world conditions? What happens if wind pushes it sideways? What happens if the load shifts? What happens if construction isn't perfect? What happens if one support weakens? What happens over time? That's real engineering thinking. And honestly, this idea applies outside engineering too. Think about businesses, relationships, careers, even personal finances. A system can look powerful on the outside, but be incredibly fragile underneath. One small disruption, and everything falls apart. That's instability. Meanwhile, something that looks simple and boring might be incredibly resilient. That's stability. And structures teach that lesson really well. Take Burj Khalifa. People look at it and think, wow, it's tall. Engineers look at it and think, how is that thing staying stable against wind, gravity, and movement? Very different perspective. Same thing with Golden Gate Bridge. Most people admire the view. Engineers think about forces constantly moving through that structure. Wind, traffic, temperature changes, fatigue, movement. Stability is always part of the conversation. And what's really fascinating? Most great engineering is invisible.
When a bridge stands safely for decades, nobody celebrates. When a skyscraper survives storms, people barely think about it. When scaffolding works exactly as planned, nobody notices. That's actually the goal. Great structural engineering often looks boring because failure never happens. And boring is good, very good, because the alternative can be catastrophic. And that's why engineers can seem overly cautious. People complain about extra inspections, extra braces, extra rules, extra calculations, extra safety checks. But those extra things are often the reason disasters don't happen. They exist because past failures taught painful lessons, usually written in blood. That sounds dramatic, but it's true. Engineering codes are full of rules created after real-world disasters. Someone ignored stability before. People paid the price. Future engineers learned from it. And that's how the profession evolves. And here's the crazy part. Most people walk through cities every day without realizing how much invisible engineering is protecting them. Office buildings, parking garages, airports, apartment towers, bridges, cranes, stadiums, everywhere. Thousands of structural members quietly doing their job, staying straight, staying stable, handling loads, and preventing chaos. That's pretty amazing when you think about it. So if there's one takeaway from this entire topic, it's this. A structure doesn't fail only when it runs out of strength. Sometimes it fails when it runs out of stability. And those are very different things. That simple idea has shaped modern engineering, and it's one of the reasons our cities can reach higher and higher into the sky. And the next time you see a tall building, a bridge, or even a simple steel column, you'll probably look at it a little differently, because now you know staying upright is a lot more complicated than it looks.